So we had a discussion now about two different kinds of waveforms, on-off keying and antipodal keying. And we saw that antipodal keying gave you better bit error rate. Why do the two exist? Well, maybe on-off keying is a cheaper solution, lower cost. So maybe when we have those three criteria, what were the three criteria that we use in a communication system? It's power efficiency. And power efficiency is like bit error rate versus EB over N0. That's kind of what I mean by that. Spectral efficiency and cost. So on-off keying, very low cost. So it might be, even though the power efficiency might not be high, it might be okay. So on-off keying, that might be one of the reasons. Now we're going to talk in another way about choice of waveforms, because there are many waveforms which may have the exact same representation in signal space, but may practically be better, and practically especially in terms of impairments due to non-ideal equipment. And that is the second discussion we're going to have now. And so this might affect a little bit the power efficiency, because power efficiency means that that bit error rate curve that we're thinking that we're following, it better be accurate. Because what happens if we have intersymbol interference? We've talked about that already. What if this impairment comes up because we have non-ideal conditions? Then maybe we're not getting the power efficiency that we think we are. So what I'm going to discuss with you now is how we can choose the waveform instead of being that nice rectangular wave. If we use another waveform shape, which would have the same representation in signal space, theoretically exactly the same power efficiency, but these Nyquist pulses might be more effective at avoiding intersymbol interference, so that even if I had components which were non-ideal, it would be more likely to approach this ideal relationship that I have an equation for if I use a pulse shape that's a little different. So we're going to talk about pulse shaping, and in particular about Nyquist pulses, in order to avoid intersymbol interference. So intersymbol interference is discussed in pages 104 to 151 in our textbook from Sklar. So before I dive into that, there are some things in the textbooks which I think might help clarify some understanding of what I mean by avoiding ISI and this technique of pulse shaping. Let's look at a system, a block diagram of a communication system where we take filters to represent the different operations that are going on in our system. So we're going to talk about the transmitter, the channel, and the receiver, and each one of them is going to have a filter to represent what's going on. For instance, let's look at the transmitter. Here the X's represent the logical data, logical 1, logical 1, logical 0, for instance. And here there's no shape. Now I use a filter to represent the shaping that I'm going to give to these symbols. So I could make each one of them to be a rectangular. So this filter could put in an impulse and come out with a rectangular pulse, or any other shape I want to use. And so this is the transmit filter. Then we have the channel filter, and this is also typically represents the transmission media limitations. For instance, if I used a twisted pair which had a limited bandwidth, maybe I would represent that as a channel filter. Then the receiving filter is the receiver that I use to limit noise, and I would usually use a match filter. So what exactly am I matching to? A match filter would actually want to take whatever shape I am transmitting, this symbol shape, but that symbol is going to be changed by the channel, especially if I have a bandwidth limited channel. So what I really want to match to is the total, because it's what is of the signal is allowed to pass through the channel that I really want to match. So sure, we would want to match the combination of these two filters. Of course, it's a linear system. It would be HT, H transmitter times H channel, and that would be what I would match to. So sometimes I just have one equivalent filter that I use for this system. And so I take all of these together and call them an effective filter. And then what I add is noise, which is band limited noise. And then I could do my sampling and my detection. And then this total effective filter would be the concatenation of all three. And like I said, I would use an equivalent noise for my simulator to make sure everything was fine. So that is one way of representing the system, is just to have one effective filter and talk about that. So remember, the system, the receiver sees both the channel and the transmitter, so the receiver should really be adapted to the combination. Problem is, with the channel, we might not know what it is. You know, we want to design an arbitrary communication system. Maybe we want a general one, or maybe it's just simply not known. Or maybe it's just a perfect channel. That for our channel, the bandwidth is so small that, for our system, the transmission bandwidth is so small, it's much smaller than the bandwidth of the system, like in an optical fiber or something. If I was sending data not too fast, well, then it's like a perfect channel. Then it would be like an all-pass channel. So this idea of a matched filter, it's kind of idealized in some some aspects. We have to know what it is. And in some cases, it's not really necessary. So it just depends on the situation. So don't get too concerned about these niceties to begin with. So sometimes, if for instance the channel was a perfect channel, we would say that the total effect would be the combination of the transmit and the received transmitter. And so what I'm going to be talking about today is really sort of this situation of the perfect channel. So I'm going to assume that the channel is not taken into account. Let me put it that way. That when I transmit, my receiver is going to just match to what I transmit, and it's going to sort of hope that everything goes well in the system in between. So in theory, any waveform can be exploited if I just simply have the criteria of maximizing the signal-to-noise ratio, because the signal-to-noise ratio is maximized by the match filter. But I do need to have a channel that doesn't crush the signal, that isn't so limited that it destroys the channel. Now, there are practical imperfections in a practical channel that you have to take into account, and that these imperfections can cause intersymbol interference. So this is what we're going now to describe, is what kind of transmitter pulse shape can I use so that this approach of limiting the effect of the channel is likely to succeed. So it's really a strategy to try and shoehorn the real system into this mathematical description of a system with ideal components. So in that case, what I'm trying to discuss today is not how to deal with intersymbol interference, but instead how to avoid intersymbol interference. We'll see later with equalization what we can try and do when intersymbol interference is present. But now what I'm trying to do is, what can I do to choose my waveform shape that will simply make it easier to avoid intersymbol interference? So just a brief recall of our discussion of intersymbol interference. The channel is always bandwidth limited. The signal is always time limited, which means that you'll get some pulse stretching going on. You know, the reality is it's not that extreme, but there are always some filtering effects. And if the filtering effects are extreme, then we'll have a lot of pulse stretching, and this leads to overlapping impulses, which leads to intersymbol interference. This was the slide that tried to illustrate what intersymbol interference is. So a bandwidth, time-limited pulse gets expanded. It overlaps with the next pulse. Because of this overlapping, we get some distortion, and this distortion may cause us to make poor decisions on which symbol was transmitted. So we want to avoid intersymbol interference. How can we avoid intersymbol interference? Well, what we'd like to have is that when we do our sampling, at the sampling time, if a previous, like let's look at the last symbol here. When I'm sampling, then this dotted line represents the sampling time. I'd like to just see the component from this pulse. So here, this symbol is extending into the time of the new symbol, and there's a contribution here from this symbol, which is not the symbol I'm trying to detect. So if this contribution was 0, well, then it wouldn't matter. It could be something that, you know, is non-zero outside of its own symbol interval. But if its contribution at the sampling time was forced to be 0, well then it wouldn't hurt me. And that idea is the definition of a Nyquist pulse. A Nyquist pulse is a pulse which goes through 0 for all sampling times, except of course its own. When I go through the sample for this symbol, previous symbol, I want to get something that's not 0 at that time. But at every symbol sampling time afterwards, I want it to pass by 0. Therefore, it won't contribute to the next symbol's detection. So the definition of a Nyquist pulse is a pulse that goes through 0 at all sampling moments except time equals 0. So if V is a Nyquist pulse, then Vn of t, where t capital T is the sampling time or the symbol intervals, it would be 0 for all n except for n equals 0. Definition of a Nyquist pulse. So Nyquist pulses, what's nice is they do not contribute to ISI. So we're not saying that it's non-zero outside of the interval of a symbol. We're not saying that. We're just saying that at sampling times, it passes through 0. Again, here are the sampling times, and at these sampling times, it passes through 0. So I'm not forcing it to be like this. I'm not forcing it to be, non-zero only in a specific interval. I'm saying it can extend, but when it extends, at the sampling points, it passes through 0. Okay, so great. So Nyquist pulse, here's a definition, because if I had something like this, it wouldn't cause intersymbol interference. So what are some Nyquist pulses? Well, an NRZ pulse is a Nyquist pulse. If I do force it to be 0 outside of a symbol interval, well, then clearly I've represented that. I've met that criteria. Of course, maybe I'll get slammed by the channel, but by the definition, that's a Nyquist pulse. Another Nyquist pulse is the sinc function. The sinc function has got the sine function in the numerator, and this numerator is periodic, and that forces it to pass through 0 at the sampling times. And because I'm dividing by the argument of the sine function, I get the sinc function, which is not 0 at time equals 0. At time equals 0, these two things even out, and I get a 1. I will be talking about a third type of Nyquist pulse, which is called raised cosine, which is a very practical, highly frequently implemented pulse shape in communications, which meets the definition of a Nyquist pulse. So I'll be talking about that more in a few minutes. Lastly, I'm going to talk about something called a root raised cosine pulse, which is not technically a Nyquist pulse, but it sort of is often discussed with it because it's very closely related to the raised cosine. So let's talk about square pulses and why square pulses are not necessarily good. Here's a square pulse in the time domain, and we're going to look at the Fourier transform. And the Fourier transform is a sinc function in the frequency domain. And the problem with this goes back to our original discussion in theory, time-limited, infinite support in the frequency domain, which means that it's always going to get distorted because it'll always be cut off. Of course, if most of the energy is passed, it won't have a big effect, but still the roll-off of this is fairly slow in a sinc function. It goes as 1 over x as the decay for higher frequencies. So fairly slow roll-off for the side lobes, fairly large bandwidth, fairly large side lobes compared to other solutions that we're going to look at. Now let's look at the second choice of a Nyquist pulse. Here's a Nyquist pulse in the time domain. Okay, so now in the time domain, it no longer has finite duration in the time domain. That means I have to start at minus infinity, start up my sinc function, and let it run until plus infinity. Of course, I'm never going to do that. I'm going to truncate it, and it'll be an approximation to the sinc function. But this is more or less the pulse shape I'm suggesting that we use. And now if I look at the Fourier transform of this sinc pulse in the time domain, I get a lovely, nice, rectangular spectral density for the signal in the frequency domain. And it's very nice because it's compact, so for sure the bandwidth is finite in this choice. So this actually is the Nyquist pulse with the narrowest bandwidth. So if I tried to do any other shape in the time domain and respected that it periodically passed through zero, the one that occupied the least spectrum would be this pulse. Because of that, it's also often called the ideal Nyquist pulse. So it's ideal only in the sense of spectral efficiency. But that's the nomenclature you'll see in the literature. So let's think about this ideal Nyquist pulse, which occupies the minimum bandwidth. So if I were to be sending a symbol rate of 1 over TS, according to this expression here, where we have the time here of the pulse, and we look at the width here, just from this Fourier relationship, we know that the bandwidth for the minimum bandwidth I need would be to use this ideal Nyquist pulse, and it would be 1 over TS, the symbol time, or that would be the equivalent of the symbol rate, RS, the symbol rate, how many symbols per second I'm sending, divided by 2. So if I were going to say that, if I were to define now spectral efficiency, one way of defining spectral efficiency is to say it would be the symbol rate, number of symbols per second, divided by the very minimum bandwidth I could occupy. And therefore, it would tell me that the best spectral efficiency I could possibly get would be RS divided by W min, which would be equal to 2, or 2 symbols per second per hertz. So remember that the 3 criteria for examining a communication system was the power efficiency, the spectral efficiency, and the cost. And now I'm giving you the first time we're discussing spectral efficiency. And so now I have a pulse shape, or I know I've defined the pulse shape with the minimum bandwidth, and this minimum bandwidth is the symbol rate divided by 2. So now I can say the most spectrally efficient I can get for this signal shaping is 2 symbols per second per hertz. We saw the typical bit error rate curve being a waterfall curve. Here are 2 curves. The solid line here is closer to the origin. It's the bit error rate which is better performing than the other one. But in these projections, we always assume there was absolutely no intersymbol interference. So qualitatively, what happens when there's intersymbol interference? Well, when there's intersymbol interference, this idea of stronger EB over N0 always giving you better bit error rate gets violated. Because when I have intersymbol interference, even if I make my signal stronger, it's the signal that is interfering with itself. So it doesn't really help. So after a certain point, I get what we call a bit error rate floor. That this sort of evens out and I'm no longer getting an advantage even though my signal to noise ratio is getting higher. So that's one of the reasons we don't like intersymbol interference, is that we can no longer get arbitrarily low bit error rate by making a stronger signal, that we run into a problem that we cannot overcome.